Hello, everyone. My name is Ashwini Deshpande, and I'm the director of the Center for Economic Data and Analysis, and I'm a professor of economics at Ashoka University. I'm very pleased to welcome you to the second CEDA lecture on algorithmic bias, what it is, and what the potential solutions are. I should begin by saying that we are holding this recording, this lecture, in the midst of a very grim situation in India. And we were wondering whether we should go ahead with this lecture or not, but we decided to go ahead because we thought it would be some relief, a welcome diversion for some of us who have just surrounded by grim news all around. So to all those in the audience, if you have loved ones who have not been well or facing difficulties, my sympathies and my best wishes from all of us at CEDA. All of us are struggling in different ways, and this is the time to come together for solidarity, and which is what we see actually, millions of Indians helping each other in this time of, dire need. And that's what we feel proud of as Indians. So let me get started, and I'm very pleased to welcome and introduce Professor Manmohan Aseri, who's a professor at the University of Pittsburgh. Professor Aseri works on a variety of topics, including algorithmic bias. And we started talking a few months back about the possible uses of this new branch of research to India, because increasingly, even in India, our lives are determined by algorithms. When we log on to social media or Facebook or Twitter, the feed that we see on our screens is customized to who we are. Our searches, the keywords that we look for, what are the typical items that we click on, all these get stored as algorithms, and items are presented to us accordingly. So to a large extent, our digital lives are determined or shaped, not determined is a strong word, perhaps shaped by algorithms. And people believe that if a machine is doing it, it would be free of bias. Human beings can show bias or be discriminatory, but perhaps if machines are doing it, if it's algorithms, that's how, that automatically happening, perhaps those would be free of the discriminatory biases that guide human decisions. Is that really true? So we have Professor Aseri, who will take us through what algorithmic bias means and whether it exists, is it a real thing, and what can we do about it? Professor Aseri, thank you very much for joining us.
Thank you, Professor Deshpande, for the kind introduction. I hope I will live up to that. And thank you, everybody, for coming to this talk. I know the situation in India is pretty grim, and it feels really odd to talk about anything other than COVID-19 these days. But I hope, as Ashwini mentioned, that this will be a good break and a nice distraction for all of you to think about something else, at least for a while. So let's start. You are all, let me share my screen, yes. All right. So let us start with this algorithmic bias. Today we will talk about it. In plain English, what algorithmic bias means is that when algorithms try to mimic the human behavior, they also try to mimic the notorious side of us. We humans tend to have a lot of stereotypes, a lot of biases and all that. And algorithms will learn these biases, and also, they will amplify that. And in fact, algorithms can go 2 steps further, and they can be biased even when they're learning from completely neutral humans. That can happen because of some statistical reasons that we will talk about later. And so let us start with algorithmic bias. And so before we worry about these algorithmic bias and all that, one thing that we should be asking ourselves is that what has changed? Why are we talking about it new? Why are we worried about it now? because algorithms have been around for decades now, and why are we worried about it now? And typically when I ask this question, the common response that I get is that we are using algorithms more often, we are using them in more places, we are using them in more systems and all that. So let me tell you that more is not the right answer for that. There's something which has fundamentally changed, and there's something which is binary. There's something which is something which we were not doing earlier, and we are doing it now. So the change is that we are moving from something called design systems to something called learned systems. So for example, if you think about aeroplane, when you fly in an aeroplane, most of the time that aeroplane is on an autopilot mode, so which is an algorithm running that aeroplane. And this has been happening since the First World War, because people had to fly long distance, and the pilots used to get tired and all that. So this aeroplane is a design system because a lot of aerospace engineers have contributed their engineering knowledge. A lot of pilots have contributed their experience to design these systems. They basically handcrafted these kind of airplane systems. And because these experts have designed this system, uh, these systems tend to be very robust. If anything is going wrong with these systems, these experts will come to know what is going on, what is going wrong, what is why that wrong is happening, and how to fix that. Now compare that with today's self-driving car. Now a self-driving car is a learned system, because none of the driver is actively participating in development of the algorithm that will run the self-driving car. The way a self-driving car is being developed is that you observe the actions of a driver, when the driver turns left, when the driver turns right, when it applies brake and accelerator and so on. And you collect millions of such observation. And then we have methods to apply on this observational data and extract the driving knowledge from that data without asking a single question to the driver about how a car should be driven. And this approach of learned system, of developing a system or machine learning system, has been a massive success. One, because it is low cost. You don't need expert drivers like expert pilots and aerospace engineers to guide you how to develop the system. You have algorithms to learn from the data automatically. So they tend to be very low cost. But more importantly, these systems, these machine learning systems or learned systems, tend to be more accurate compared to designed systems, because they can learn very subtle rules that we humans tend to use in our subconscious, but we are unable to articulate. For example, many times, when you hear about a wrong or an incorrect grammatical sentence in Hindi or English, whatever, you will find that it is grammatically incorrect. But if you ask me what is exactly the grammatical rule that is being violated, nobody will be able to tell that. So we humans are very good at deciding what is right and what is wrong, but many times we are unable to articulate why that is the case. So if in that kind of a situation, when we humans are unable to articulate the rule that we are using in our subconscious, you cannot design that rule because you can't articulate that. But in designs, in the learned systems, you don't need to articulate. The algorithm will learn all the granular rules that we are using in our subconscious and will learn all that. But the dark side is that because the algorithm can learn all these subtle subconscious things in our mind, we humans tend to have a lot of stereotypes, a lot of subconscious biases and etc. in our mind, which we don't know that we have that. So these algorithms are very good at picking those subtle biases and subconscious biases that we have in our behavior. And but these systems tend to be very highly accurate, but there's something wrong with this system. There's a small problem that these systems tend to be black box algorithm. And you will also notice that most of the self-driving cars are being developed by machine learning companies rather than the automobile companies. This is because you don't need to be a domain expert to develop through this approach, by machine learning approach or learn system approach. The dark side is that these algorithms tend to be black box algorithms. And I mean, all these neural nets or random forests, whatever you talk about, these are all black box algorithms, but they are highly accurate. And because of this, it becomes very difficult even for the creator to find problems in these kind of systems. And that creates fertile ground for them to sort of hide their deliberate malpractices if there are any. So this becomes a very difficult challenge for people to solve. And one of the thing that we will focus in our talk is the discriminatory behavior exhibited by these learned systems. So let us start with some examples. And in each example, we will first think about that there is a bias, why the bias is happening. And having understood why the bias is happening, what's the source of it, we will try to see how we can possibly fix that bias. Okay. So let us start with the first example. This is kind of very related to what is, I hope you will be able to relate it because we all use Google Translate. This is bias in Google Translate. So for example, if I write this text in English, he is a nurse and she is a doctor. And if I try to translate this text in Hungarian, for example, then I get this text. Now, I don't know Hungarian language, but I know a simple fact that if I take this text, copy it, and translate it back into English, I should be getting the same text, right? Simple logic. And when I do that, when I take this text, you can visually verify that these two texts are same, even if you don't know Hungarian. You see that there is something strange happening here. He is a nurse has been replaced by she is a nurse, and she is a doctor has been replaced by he is a doctor. Now, this was pretty strange for me when I encountered this. I found this example in some newspaper somewhere. I wanted to understand why is this happening. So I thought, okay, I don't understand Hungarian, so let me do the same thing in Hindi, which is my native language. So I did that in Hindi, and I wrote this English text and converted it into Hindi. I can see that this is a correct translation. So far, so good. But when I translate it back, the same problem happens again. He is a nurse has been replaced by she is a nurse, and she is a doctor has been replaced by he is a doctor. Now, because I know this language, Hindi, I can tell you why it is happening. What is the source of the bias in this case? Those of you who understand Hindi, they know that in Hindi, the Hindi translation of he and she is actually the same word, which is va. So when you translate from English to Hindi, you lose that information, he or she. So therefore, when you translate it back into English, that lost information cannot be recovered. Therefore, the algorithm is doing what happens on an average, like what is true on an average. So on an average, or in most cases, apparently most nurses are she and most doctors apparently are he. And therefore this is what algorithm is doing. But algorithm deterministically does that. So that there will never be a case in which algorithm will use he for nurse and she for doctor. And that is where the problem is, because we humans might have some randomization there, some kind of, we might use he or she, we might be more neutral, but algorithm, because of their deterministic nature, they may not do it. But this was my intuition that I was thinking that this is the source. So I wanted to further verify this. So I thought, let me find some example in which this problem will not happen. Okay. So I found in Chinese, those of you who know Chinese, most of the time there are some Chinese friends in the audience, so they can verify that this is a correct translation. So in Chinese, this thing doesn't happen. So he is a nurse he is a nurse and she is a doctor is still she is a doctor. And the reason I have verified this with my Chinese friends is that in Chinese, he and she are represented by different syllables. And even if you don't know Chinese, you can visually verify that this character in the beginning is slightly different from this character. So you can visualize that. So then we are kind of confident that this is actually the source of bias. Then once we understand what is the source of the bias, then we can sort of think about how we can possibly fix that. Now, a simple way to fix that is that simply use he/she as we use in our conversation, as we humans solve this problem in our day-to-day life. The other more algorithmic way of solving it, or more programmatic way of solving it, is that you randomize in proportion to the representation in the group. For example, if nurses mostly females, and let us say if 60% of nurses are females, then 60% of the time you should be using she here, and 40% time you should be using he here. You can flip the coin, you can randomize it according to the proportion of in the population. So that is one thing you can do. But surprisingly, I've been giving these kind of examples and talk and all that since past 2 years, but I haven't seen this problem being fixed. I checked it before this talk, and still it is happening. I don't want to blame these companies because they are, doing their best. These are, difficult problem to fix, and most of the fair ML literature and research in fair ML is actually being conducted by people working in industry. Companies like Google and Amazon, Microsoft are working in that. So I don't want to blame these companies and jump the gun. My guess is that these are difficult problem to fix. For example, even if you fix it for he and she, and in the case of nurses and doctors, there can be like millions of such combination where you might find this kind of bias in language translation. So this is a difficult problem to fix. That's what my guess is. And it's difficult to fix also because these are not design systems, these are learned systems. So because these are not design systems, you don't get too much of input from the user end and accommodate each and every input. No expert is really involved in designing these systems. So because you're learning directly from the data, you have minimal, interface dealing with the user correcting the system. Okay, so that is one of the reason we are facing this problem, because it's a completely different approach of designing or developing new systems in today's time. So this was kind of, harmless discrimination. It's not completely harmless because it builds our stereotypes and all that for different groups, but still it is not as serious as, the next example that I will take. The next example is about a software, a Compass software, which is actually used in real courts in America to decide whether an arrested person will reoffend or not. So you predict about an arrested person, and you find the probability of that person reoffending a crime. And using that probability, you want to decide whether to release that person on bail or not. Okay, this is a real software used in real courts in America. So let us take an example of this software. In this picture, on the left-hand side, you see a white man who has been given a low risk score by the algorithm, which is 3. And this low risk score means that this white person will not reoffend or recommit the crime. On the right-hand side, you see a picture of black female, and the algorithm has given a high risk score of 8 to this black female, which means the algorithm thinks that this person will go on and reoffend or recommit the crime. But if you look at their, crime history, then you see that this person on the left-hand side has committed 2 armed robberies, 1 attempted armed robbery, and still the algorithm thinks that this person is low-risk person and will not reoffend. On the other hand, this person, the black female, has committed only 4 juvenile misdemeanor. So those of you who are not from India, the technical definition of juvenile misdemeanor is that if you, resist to some kind of law enforcement procedure, for example, if you resist to, searching your car, or if you resist to getting arrested, for example, then it is a juvenile misdemeanor. So technically, there is no crime involved in that. So this person has committed only 4 juvenile misdemeanor, and still the algorithm thinks that she will reoffend. And not just that, after that, these people were observed for 2 years to really verify whether they go on to recommit the crime. So this person on the left-hand side actually went on to commit a grand theft. On the other hand, this person did not commit any crime. So this is kind of like really serious. So now let us dig deeper into why this problem might be happening. So now that we understand that there is some bias happening, let us first understand why it might be happening. What is the source of the bias? So the problem is that the algorithm is failing differently for black versus white. To be precise, the false positive rate for blacks is much higher than whites. So those of you who are not from machine learning and like hearing false positive things are for the first time, in machine learning, there is something which is positive class. Positive class means the class which we are trying to predict. For example, in this case, the positive class is uh, whether somebody will re-offend or not, or recommit the crime or not. So we are, if somebody recommits the crime and we are classifying that person as reoffender, we are classifying them as positive class. So if you incorrectly classify somebody as a reoffender, that's a false positive instance. So it turns out that the false positive rate for blacks is much higher in this case, which is 44.9%, and that false positive rate for whites is only 23.5. Now, the plain English definition of this is that more innocent blacks are being jailed compared to innocent whites. So if you are innocent black person, you have much more likelihood of getting into jail compared to an innocent white person by mistake. Okay, so which is why it is false positive. And the other thing is the false negative rate for blacks is much lower than whites. So let us say you are a black person and you have actually committed the crime. There's a small likelihood that you will escape, but that likelihood for you is much lower than the likelihood for a white criminal, because the false negative rate for blacks is much lower. So it means that fewer guilty blacks are released compared to guilty whites. So it means that blacks are losing on both type of errors. If you are a black person, the type of error which you would like to be low for you is actually higher for you, and the type of error which you would like to be higher for you is actually low, right? So this is what is happening with blacks, and they're losing on both type of errors. But you also notice that because one type of error is higher for blacks and other type of error is low, the overall error rate can actually be same for blacks and whites. And therefore, if you simply look at the overall error rate, you might miss this kind of a discrimination. Uh, and this is why, the company which develops this software actually kind of uh, argued that our software is not, discriminatory, because it makes similar type of errors for both blacks and white, because they were calculating the overall error rate, and they missed the argument that if you simply calculate one particular type of error, it can actually be different. So how do we solve this? Now, a simple way to solve this is that you somehow match these false positive rates. Somehow you do something so that the false positive rate for blacks and whites are same, or the false positive rate for false negative rate for blacks and whites are the same. And how do we do that? Let me harp on this point that, no matter what kind of algorithm you're using, no matter what method that you're using, whether you're using simple logistic regression or complicated methods like neural net, random forest, ensemble method, or whatever algorithm that you're using, in the end, that algorithm is going to give you some probability. For example, it will give you some probability of re-offending to be 95% for some person, and for somebody else it will give 60%, for somebody else it will give 10%, and so on. But algorithm will be done at that point. After giving the probability, algorithm is done. Now it is in your hand to decide a cutoff. For example, I can decide a cutoff of 90% and say that anybody whose probability of reoffending is more than 90%, I will call them reoffenders, and otherwise I won't call them reoffenders. Now think about it. If I raise this cutoff from 90% to, let us say, 99%, I will be more conservative. I will be all those people who I will call as reoffenders, they are going to really, really reoffend. I'm that much sure about them. So my false positive rate will go down for that case if I raise my cutoff. And but in that case, I will have a lot of false negatives. I will be letting go a lot of people who actually had very high probability of reoffending, but I did not classify them as reoffender. Like for example, 95% probability person, I will classify them as not reoffenders. So my false negative rate will go up. But the point that I'm trying to make here is that by choosing these cutoffs, you can choose the false positive rate. Therefore, if I ask you to match the false positive rate for blacks and whites, you choose two different cutoffs in such a way that the false positive rate for both the groups are same. And this is what the theme of the literature is, that you should be matching some of the kind of error rate, some either false positive and false negative or combination of these. So this is where the literature is focusing on about how to fix this kind of a problem. Okay, so by adjusting these cutoffs, you can actually make the system slightly fair. But remember that just because your system is fair according to false positive rate, it may not be fair according to other criteria. In fact, we will talk about later on about a celebrated result in fairness literature, which is called impossibility theorem. The name itself suggests that it is impossible, to satisfy multiple fairness criteria given some conditions. So just because you are choosing to satisfy false positive rate, or you are choosing to match the false positive rate across groups, doesn't mean that you will be able to satisfy other fairness criteria. So typically my recommendation is that the fairness notion which is true for Amazon may not be appropriate for Google, may not be appropriate for governments, may not be appropriate for Microsoft and so on. So every company needs to think about what is the most appropriate fairness notion for its context given other stakeholders, and stick to that fairness notion, and make sure that that fairness notion is satisfied. Because tomorrow if somebody comes up and says that you are doing unfair, so that you can come back and say that we are fair according to this criteria, and then you should be able to justify why that criteria is the most appropriate according to your context. Because every company's context can be different. In the case of like Compass software or predicting reoffending, according to me at least, false positive rate matching seems to be more appropriate. But in loan granting, for example, you can have true positive rate or any other criteria. So depending on what context you are working on, you can choose these fairness criteria. That is, somewhat a good thing about algorithmic bias, that you can choose different fairness criteria in different contexts. This is very different from the fairness notions that we have in physical world, where we have one fairness notion across the board for all contexts, mostly. So let us now look at some of the literature in that. Having seen these two examples of algorithmic bias, now let us try to generalize what are the general sources of algorithmic bias, and then we will talk about what are the general methods of solutions to solve these problems. So the most common, the reason of algorithmic bias is underrepresentation of some groups. For example, minorities. Minorities means, for example, blacks in the US, they are minorities. They're only about 13% of the population. So 13% of the population means there are hardly going to be 13% data points corresponding to them in the data sets. So because there are fewer data points related to them, algorithms are going to be less certain about them. It will make more errors about them. So it is just that because you had fewer data points corresponding to one group, so algorithm becomes less accurate about them. But some groups are not minority in the physical world, but they are minority in the data. For example, women are not minority. They're half of the population. But typically, women are seen as minority in the data because historically, fewer economic opportunities have been given to them, like fewer jobs, fewer employment, fewer education opportunities, fewer loans have been given to them. So if you look at all that data, there will be fewer data points corresponding to females. So again, the same logic you can use, because there are fewer data points corresponding to women, algorithms are less accurate about them, and it makes more errors about them. So this is the most common source of error, source of algorithmic bias. A more, unintuitive or like new to me when I was looking at the literature, this is something which was surprising to me, is that many times we have wrong objectives to predict. For example, in all kind of prediction problem or in all kind of algorithmic problem, you have to decide a goal. Algorithm needs to be given some goal to achieve. In the Compass software, you had a goal of predicting whether somebody will reoffend or not. right? That was the y variable, those of you who understand algorithms a lot. So many times we tend to have wrong objectives. For example, if you try to predict arrest, that is not equivalent to predicting crime. If you because those areas where there is more policing going on, there are going to be more arrest in those areas, obviously. And in fact, if you try to predict even conviction, that itself is also, not equivalent to predicting crime, because courts make errors all the time. And if you simply because you predicted somebody's conviction doesn't mean that you actually predicted the crime. And the truth is that the committed crime may not, the truth about the committed crime may not actually be available. Maybe the only person who committed the crime is the only one who knows who actually has committed the crime. Nobody else will know. So, and that person is not going to tell you. So many times we tend to have wrong objectives. So this is another like under the radar kind of a source of algorithmic bias. And third source of algorithmic bias typically happens is that there's a feedback loop. For example, the decisions in this period will influence the data that I will collect in the next period. So that is what is the feedback loop in the algorithmic bias. For example, in predictive policing, if you are policing one particular area repeatedly, then you are going to have more conviction and more arrests from that particular area. And then you will put more policing, and that feedback loop will continue on and on. So these are, three high level sources of algorithmic bias. So now let us talk about what kind of solutions that exist. So at a high level, you can think of a solution consisting of these three pieces. Any algorithm has these three pieces: that you first have some input, and that input you transform, or if you feed into an algorithm, and that algorithm will transform that input, process that data, and generate some output like the probabilities, which I talked about earlier. So you can fix each of these three steps in different ways. So first, let's talk about how to fix the input. For example, one way to fix the input is that you can simply remove the sensitive variable. You can remove the gender variable, you can remove the race variable and all that. And you can, by doing that, you don't ensure that bias will go away, because even if I don't give you my gender information, but I give you 100 other attributes, using those 100 other attributes, you can pretty much, very confidently find out what my gender, my race, etc. is. So this solution will reduce the bias to some extent, but it is not perfect. So you might have to use some advanced, statistical methods to uncorrelate the other 100 attributes from the sensitive attributes and use the uncorrelated data. And then there is a big thing which kind of goes under the radar about fixing these algorithms, is that why not fix these algorithms and make them, transparent? In the beginning, I talked about that these algorithms or the learned systems or machine learning systems tend to be black box algorithms. So because they are black box, you don't have understanding of how the algorithm is working. So one way to fix this problem is that you can make these interpretability methods, you can make these algorithms a little bit more transparent by using some interpretability methods, like lime and shape is one of the interpretability method, which will give you some variable importance score about every variable. So if your gender variable is playing a role in the decision, or the race variable is playing a role in the decision, then the lime and shape will figure out how much weightage that variable is having, how much role that variable is playing in the decision. So then you can probably remove those variable, or you can do something about it, or you can think of it like that why gender is or race is playing a role, because it may be correlated with some other variable. The other way is that counterfactual explanation about interpretability methods. Counterfactual explanations are that what will change the decision. So for example, if I have been denied a loan, then what will change that decision means if this kind of explanation will give me some kind of statement that if my income was 20,000 higher, then I would have been granted a loan. Or if my education was 4 years higher, then I would have been granted a loan. Something like that you can do to make this algorithm better. And another way to fix this algorithm is to have diverse developers of algorithm. So therefore, in Silicon Valley, there's a big demand of women in the algorithm teams, and they are trying to make the teams as diverse as possible, so that these different people from different background can cover the blind spots that other people might be missing. Now, even if you fix these two steps, even if you fix the input, even if you fix the algorithms, there might still be some leftover bias, and that is what was happening in the Canvas in the Compass software case. And in that case, we use a brute force method that you adjust the cutoff. Now there is already some leftover bias, so you adjust the cutoff and match the error rates. Now you choose what error rates to match or what fairness criteria to use. And that is where most of the focus is of the literature. Most of the literature focuses on this step. But I wanted to highlight that there are two other steps before that. We can focus on them also. And the deeper you fix the problem, the lesser is the need to fix at the output level. So now let us talk about some literature in this case. So if you look at the literature, the literature is all around about scattered all around. So there are about 21 definitions of fairness. So when I was reading it, it took me a while, to find some pattern in them. So there is some results like impossibility results, which means that there are certain condition, if they are not satisfied, it is impossible to satisfy multiple fairness criteria. So literatures, so it might be difficult, for you to satisfy multiple fairness criteria, but there is some method in this madness. You can classify all these 21 definitions of fairness in two different classes. One is individual fairness notions and other is group level fairness notion. Individual fairness notion simply means that you use the same standard for all the individuals. For example, the same cutoff should be used for all individual. Like I was giving you an example of false positive rate, you have to use same cutoff. So all the individuals should be subject to the same criteria. Group level fairness notion is like matching the false positive rate or false negative rate and so on. So you have to equalize some group level statistics. So then you have to use different cutoffs for different groups to match this fairness notion. But that can be controversial because some group might say that making the cutoff same is actually the fair, and some groups might say making the cutoff different for different groups is actually the fair thing. So let's talk a little bit more about individual fairness. Now let's dig deeper into these two different classes. And one example that comes about in individual fairness is equal treatment, which simply says that you have to be class blind. You cannot look at the gender or race to make decision. In other words, you have to use same cutoff. And this is according to the Title 7 of the US Civil Rights. This is the current US law in the US. But the problem with this kind of fairness notions, individual fairness notions, is that many times the cutoffs can be very high. For example, in the US, if you are a bank and if you decide that anybody whose credit score is more than 750, I'm ready to give loan to them. But 750 credit score in the US can be too high for African Americans. So although you are not, deliberately discriminating against African Americans, if you use a cutoff of 750 in the US, you will end up giving loans only to whites or non-blacks. So that is a problem because in individual fairness, the cutoff sometimes can be too high, and that leads to a lot of problems. So then we talk about group level fairness, which kind of addresses the problem of individual fairness. Said in this group level fairness, there are several examples. One is demographic parity. This is very similar to the fairness notion that we have in the physical world, that if a group has 20% of representation in the population, 20% resources should be given to that group. 20% of loans, 20% of education, employment, and all that. So in the example of African American, because African American in the US are 13%, so it's 13% of loans should be given to African American, for example. And then we have other example, which is, I call it slightly advanced notion of equal opportunity. There can be slightly difference between the terminologies used in economics and the terminologies used in computer science, but let's focus on the meaning of these notions. I call it slightly advanced because it says that you don't have to be fair with everybody. You have to be fair with only good people. For example, the good people in blacks or good people in whites should have equal chance of some decision. So good people means in the loan granting example, given that a person is not going to default, the probability of getting the loan should be same. So mathematically, you have to match these two conditional probabilities, that given that person is good, the chances of acceptance should be same across the groups. So that is kind of a conditional probability which you can calculate using the historical data that you have, and that makes it like pretty exciting to see that in algorithmic bias you can have this kind of advanced fairness notion, which was kind of not possible in the physical world, because you don't have access to so much of historical data to match these kind of probabilities and calculate these conditional probabilities. So this, in plain English, simply means that good people should have equal chance. And now let us talk about, where are the gaps? If you go to some Fair ML conference, they are doing like fantastic job, and a lot of work is going on. And to my surprise, it becomes difficult to find people from academia in those conferences. Most of the work is happening by industry people working in companies like Google and Microsoft. But there are some gaps because most of the work is coming from computer science. There is something which is an opportunity for people like us in economics and business schools. So there's enough work to point out at the existence of bias, that if you point out that there is a bias, that will no longer be surprising, because now people are kind of convinced that the algorithmic bias is everywhere in all algorithms. But what is not happening, or where is the opportunity, is that what kind of intervention leads to mitigating these biases? What kind of interventions that we can do to reduce these biases? So that is where there are very few papers, and I could hardly find one paper which I want to highlight here. And this paper is about discrimination at Airbnb. So I hope you all know about how Airbnb works. And there was a discrimination going on in Airbnb, that if you are a black host or black guest, people will not respond to you. So if I'm a black person and if I book a room, the host might deny to give me a room. Or if I'm a black host, people will not apply for a room at my place. So these kind of things were going on in Airbnb, and Airbnb did some intervention which actually worked really well. So what they did was they introduced something called superhost status in Airbnb, which means that if you qualify for certain criteria, for example, if your response time is lower than a threshold, you have very good review, very star rating, then you will be given a superhost kind of status. Now, the superhost obviously benefits everybody, but the benefit of superhost for blacks was about 50%, and that for whites was only 13%. It means that a lot of benefit lot of extra benefit that blacks are now getting is because a lot of discrimination was happening, and that was statistical discrimination in nature. That was not taste-based discrimination. People just were uncertain about their quality. They were not like averse to going to a black person's house. They were just uncertain that this person might be not very good. So the moment you showed or signaled their quality, people started coming in. So that's like a pretty good way to mitigate bias, that by signaling quality. In physical world, we signal quality by education, but in the online world, there are many, many other ways to signal quality. Like in LinkedIn, you can give recommendation, or your number of connections, your reviews on websites, or many other ways to signal quality. So this is one simple way to intervene, that the more we signal the quality, the less will be the statistical discrimination. So that is where there is some opportunity. People can pursue these and kind of investigate different kind of interventions. Another one is that the theoretical, which is my favorite because I am a theoretical researcher. I use tools of game theory and other economics tools to analyze problems. Because most of the literature is coming from computer science, they don't incorporate typically the incentives of other stakeholders. For example, if I introduce a fairness notion, how will it change the incentive of the algorithm designer? How much effort that they will exert to develop these algorithms and so on. So this is the kind of uh, another sort of gap in the literature, and I try to exploit this one because this is what my strength is. So with that, let me talk about some of the work that I have been doing. By the way, how much time do I have? Am I on right?
Yeah, we got a little distracted by the description, but you can, I guess, go on for about how much time do you need?
10 minutes will be fine.
Okay, 10
10 minutes.
minutes is fine. Yeah, I think that's
Yeah.
good.
Okay, good. So let me now talk about one project that I've been doing and very excited about that. This is like recent one, and this is algorithmic bias in advertising. So there is an evidence. There is a very strong evidence about females are less likely to see employment ads. So this is a paper which recently came out in Management Science and kind of an eye opener. But the more important thing is that there is an algorithmic bias in advertising, not because advertisers are biased, it is because of something else. So let me explain what happens. So what happens is that females are considered like very lucrative customers for retailers. So if you are a retailer like Macy's or, for example, Zara in India, then the moment a female comes online on Facebook, all these retailers start jumping up and down, and they want to show their ad to the female. And the reason they do it is because there is a marketing statistic that 85% of e-commerce or online purchase happens by females. Well, there's nothing wrong in being a shopping loving person. I am a food loving person, and that doesn't make me any less of other things. But in this case, things are getting mixed. So what happens is that the moment a female comes online, these retailers bid a very high value for these female impressions to show their ads to these females. And on the other hand, there's an employer who is neutral between females and males, and that person bids the same amount for males and females, $5, for example, in this case. And in this situation, you can see that most of the time, this employer is going to lose these female impressions. And when a male comes online, these retailers don't show as much enthusiasm, and they bid a very low amount. And this employer still bids the same amount. So in the end, most of the ads of employer are shown to only males. That is the result, right? So we wanted to analyze how we can fix this kind of a problem in ad auctions, because most of the impressions are sold on ad auctions these days. So what typically happens on Facebook is that Facebook is actually addressing this kind of an issue, but they are slightly deviating from what actually should happen. What Facebook currently doing is that Facebook doesn't allow you to target on the basis of gender, race, and other demographics. So on Facebook, you cannot choose to show your ad only to females or males if you are an employment related ad, or if you are showing some education related or housing related ads and so on. So this is something Facebook is doing. So you can clearly see that this solution may not work because of the different incentives of different type of advertisers. But there's something which this Facebook's approach will solve, that if any employer is deliberately trying to show its ad only to males, this approach will solve that problem, but it won't solve the complete problem. And because it doesn't solve the complete problem, there is another solution which is being proposed in the literature, which is that you jack up the bids of employment advertiser by some amount. And that's how you will make the employer or employment ads more competitive against the high budget or deep pocket retailers. So this is what we wanted to analyze that in our paper, that let us say this is the approach that you fix, that you jack up the bid by some X amount. And how will this change the incentive of different stakeholders, and how will it, affect the equilibrium output? So the platform will jack up the bid of employer by, let us say, X amount, and this X will be chosen in such a way that the employer's ad will be shown to equal number of males and females. So this is how platform will try to fix this problem. This is what they call equal exposure problem, equal exposure fairness notion. And we analyze this, and on the surface, if you look at this problem, you will feel that the platform is kind of giving some freebie to this employer advertiser, and therefore the platform should be worse off. But it turns out from our game analysis is that the platform can actually be better off, because you see that without this gap, without this jacking up the bid, there's a huge gap between the bids of this retailer and the employer. So you can see that the retailer is bidding about 5 times the bid of the employer, and the employer is bidding 5 times the amount of retailers bid on males. So there is a huge gap. So basically, there is no competition happening for females, and there is no competition happening for males also. So by jacking up these bids, you heat up the competition, because these bids become closer to each other, and now they have to compete more fiercely to get the same number of impressions. So because of more competition, this retailer puts in more money to get more females, and because of this, the employer also puts in more money, because now it gets that more money I put in, the more X, the more will be the X, and more jack up that I will get. And because of this more money put in the system, the competition actually heats up for females. And once the competition for female heats up, the male option starts looking attractive for a retailer, and it puts more money in the males also. And then, the competition heats up for males also. So overall, both these advertisers starts putting more money in the system. And who makes that extra money? Platform is the one who makes that extra money, because platform is the one who is selling these impressions, like Facebook and all. So overall, the main result of this paper is that the platform can actually be better off with this kind of an equal exposure fairness notion. It not only makes the female more informed about these employment opportunity, it also makes the platform better off. So it is actually in the interest of the platform to make this advertising fair. That is like the main message of our paper. And many times, when I talk about these kind of unfairness in advertising, people kind of try to dismiss that hey, why is it even important? It is just advertising, and anyways, who clicks on these ads? So let me tell you that advertising actually plays an important role in our society, because they inform us about the existence of some economic opportunity that we can take. So in this case, the females are getting less informed about some economic opportunity. So if we fix this problem, then they will be more informed, and they will apply for more jobs, and then people will not complain that we can't hire more females because they're not even applying. But actually the problem may be that they are less informed about the existence of such jobs. So I think I am running out of time. So let me go to one slide that I really want to talk about. This is another paper which I wanted to talk, but that's fine. We can. So let's talk about the final, remark about this talk. Actually, in my view, there is no point, in overreacting to the situation, because I know that algorithms are biased, but so are the humans. Humans are also biased. So as long as algorithms are less biased compared to humans, we should be actually fine. But we have to make sure that algorithms are less biased than humans. And on top of that, these algorithms, unlike humans, don't try to find loopholes in the system and try to work around and do away with that. These algorithms blindly follow rules, but the onus is on us to create those right set of rules. And that is where more effort should be directed to design right set of rules. That effort needs to come from academia, from industry, and so on. But we need to design those right set of rules, and then the algorithms will be fine. And the another thing which I like about algorithms, although they are biased, but we can take care of that many times. But algorithms opens up a large possibility of fairness notions. So unlike in physical world where we are kind of restricted to only one or two particular classes of fairness notions, in algorithmic world there are many possibilities. Like you can match error rates, you can match conditional probabilities, or you can match combination of these, and you can actually tailor this thing to the context that you're working in. For example, you can use true positive rate for loans, and you can use false positive rate for bails and all that. And because this talk is about is in India, so I wanted to say something about that. One paper I read from somebody who works in Google Hyderabad in India. That person wrote a paper. I forgot to cite that. I should have cited that. But the paper says that most of the algorithms are actually being developed in Silicon Valley. Therefore, if you take these algorithms and deploy them halfway around the earth in India, it may not be the most appropriate thing to do, because there are a lot of assumptions which we make about algorithms. Those assumptions might be true for the US context, for Silicon Valley context, but may not hold for Indian context. And like data collection process is different in the US that compared to that in India. And the way you collect data introduces some kind of bias in the data, and that bias may be different in the US, and they have taken care of that kind of bias in the US when they developed these algorithms. But when you take these systems and deploy them in India, things can be slightly different. So you have to be very careful with that. So I think that's all I had, and thank you very much for your time. And any question I'm happy to address now.
Thank you, Manmohan. That was fascinating. A lot of it is, new for at least some of us. So we learned a lot, and it's a pity that you were not able to show the slides that you had originally planned to. But I'm sure that we'll get an opportunity to um, discuss with you later on over email. There are two questions that are already on the screen, which is. So Ria asks, can we use a combination of learned and designed systems?
Yes. So for example, for a while, like for 5-10 years ago, you were not able to. But now that we had these problems of black box nature of these algorithms, people have developed some interpretability methods, which I talked about earlier, like Lime and Shap methods and counterfactual explanations. So using these explanations, you can understand what's going on in this black box, and then you can choose to collect more data of a particular type to feed into algorithms. You will understand what's going on in, and that will guide your future steps about what more data, what new data you should be collecting, and that is the way you can actually guide it. So that's the only way I can think of some designers input into these systems. And I think that's the way I will look at it.
But does it happen? Have you seen examples of that
Yeah.
kind of combination of learned and designed?
Yeah, this is happening. For example, in one of the healthcare system, they developed an algorithm, and the algorithm was doing like perfectly to predict cancer. But then they applied some interpretability methods, and then they found that all those reports which actually had cancer, in the label data, the doctor has put a tick mark, and the algorithm was not actually detecting the cancer, but the algorithm was actually detecting that tick mark by the
Mm.
doctor. But you were able to find this the fact
Uh,
that the tick mark is being detected by interpretability methods. So
mm.
if those methods were not there, we would never know that this is what the algorithm is doing. And now that they have come to know that, they have taken some actions, then they are removing those data points which have those tick marks, and correcting the data and cleaning the data, and that is how it is guiding you. But in the end, learning from the data through this machine learning training algorithm will still remain the same. But what more data that we need to collect and how to clean the existing data, that will be guided by these interpretability methods.
Right. Okay, so Samir asks, should interventions to mitigate algorithmic bias be made by individual firms or by the government?
Well, I think it is too much for governments to do, and governments may not actually know the context of each and every company very well. And it turns out that the way the fairness notion which is appropriate more for Amazon may not be appropriate for Google, because they are different businesses and all that. So I would leave it to the I mean recommend to leave it to the companies and trust them, and just get them to at least follow one fairness notion which they think is the most appropriate according to their context and the stakeholders that they have to deal with. And after that, once you are satisfying one fairness notion, you will definitely not satisfy many other. Then you have to take some actions, to mitigate those things. And yes, there's one thing I forgot to mention in the talk, that a more accurate algorithm is typically better, because just to illustrate the point, if an algorithm is perfect and if it makes zero errors, it is fair from all criteria. It will satisfy all fairness criteria. A perfect algorithm which makes zero error will have, because the errors are zero, the difference between the errors will also be zero. So leave it to the companies to find out how to make these algorithms more accurate. Don't compromise too much on that, because a more accurate algorithm will satisfy most of the criteria and the gaps will be lower. But which gap is the highest and which gap they should be trying to close the most, leave it to the company, because they have other stakeholders to work with.
Right. Um, okay, so Nakshi is asking, just, can we get the complete slides on the model, or is there a working paper for this that we can share with on our on our website?
So the paper which I could not talk about, that is forthcoming in management science, but the paper which the algorithmic bias in advertising is something which will be available in a month. I will put it on SSRN, but we have the analysis. We're just writing it and wrapping it up, and slides I can share it with you after the
All
talk.
right. So then we'll put it up on our website as well.
Sure.
Okay. So Anuradha asks, if the systems are learned and learn on their own as more data is inputted, how great is the role of the algorithm creator? Will having a more diverse set of algorithm creators really help?
Yes, definitely. So that is like the first thing that we should be doing, that make the teams diverse so that they will know that what is lacking in the data. And many things which we assume in the data, are those assumptions may not hold, because before training the algorithm, we do cleaning of the data. And what cleaning processes that we apply for data is typically the guided by the team that you're working with. So what is appropriate, what is not appropriate needs to come from diverse point of views, diverse set of people. And therefore, in the US there is a huge push towards increasing the diversity of algorithm teams. A lot of females are being hired, a lot of African Americans, people from different walks of life are being hired here.
Professor Kanika Mahajan, on fair advertising, what about the retailers and employers? Do they gain from heat up in the competition?
Yeah, so surprisingly, they can be worse off. Yeah. So the both the heated, because of heated competition, both the advertisers are actually worse off in our results. But the main holder which we are focusing on, that is females. Females are better off. So females are shown more employment ads. That is, but the overall goal of entire fair advertising was to make that stakeholder better off. But of course, when you make systems fair, some group will have to give away some utility to increase the utility of some other group. So of course, both type of advertisers are worse off, but the platform is better off. And that result is important because in the end it is the platform who will decide whether to implement some kind of fairness on advertising or not. And other stakeholders are just participants. So for Facebook and for Google's and all that, you know our results kind of suggest that they will be better off by introducing these fairness notions. But this is a theoretical paper. It is a nice hypothesis which other people can probably test it.
Test with data. Okay. Bertrand asks, referring to the discussion on targeted ads,
Hmm.
Are there examples of biased algorithms generating positive outcomes? For example, an algorithm which targets a black person for career orientation in entertainment industry rather than banking because that's where they might have a higher chance of success. Does making this algorithm fair, uh, then does making this algorithm fair a question of morality and ethics, or does it make things worse?
Well, that's kind of subjective. So, it is very difficult to find out what we want to make fair. Currently, there are three things which Facebook tries to make fair of, because like education, employment, housing. These are the three types of advertisements for which Facebook is trying to, implement some kind of fairness. They currently don't allow you to do targeting on the basis of demographic attributes like gender and races, but you can become more granular, like in employment, what type of employment, like entertainment industry employment versus music type of employment. You may have to design more, tailored fairness notions. But that is, subject to debate how much Facebook wants to go deeper into these things. So at some point we will have to choose where we draw the line and stop there. But yes, if they want it, they definitely can do it.
Siddharth Maji, great talk. I had a question. We read about big tech leaders being called for senatorial hearings in the US. Is
Hmm.
algorithmic bias and related issues also a key consideration for senators and other such regulators' representatives?
Yes, definitely it is. It is a big concern here, and and but let us not blame these companies. I would actually won't go ahead and blame these companies, because these are difficult problems to solve in the first place, and they are putting in their best effort. They have hired the best resources, and if you go to conferences, as I mentioned earlier, most of the participants, most of the papers are written by people working in the industry, so they are doing their best. And I am hopeful that within the next 10 years or so, we will have a world which is run by algorithm largely and run by better algorithms, actually.
Okay, so there are lots of questions. Do you have another 10 minutes or are you?
Yeah, yeah, sure, we can go
Okay,
ahead.
so we were going to end now, but we'll just, quickly, so sort of short answers. And what we'll do, everyone, is also, share Professor Aseri's email. So if it's something that you want to discuss later on over email, please feel free to reach out. Okay, Rajiv Ranjan says that this talk was great. Congratulations to the organizers. The question: what role do states, governments can play in regulating AIML? Is there a role for data agencies like national statistical offices?
Yeah, that is very good question. And one is low hanging thing that they can do, which government can do, is that make the data available, because unless the data is available, you can't do much. And the more data is available, the more accurate will be the algorithm. And the more accurate the algorithm is, the better, the more criterias of fairness it will satisfy.
Mm.
So the first thing the governments and the other institutions can do is make the data available as much as they can. And what the government should not do is, intervene into every company and all that. Leave it to the company and trust them, and at least make sure that if they really want to ask something from these companies, at least ask these companies to pick one fairness notion from the literature and stick to that, and justify why they kind of chose that fairness notion and why that fairness notion is the most appropriate according to them. And because as I mentioned, that each fairness notion may be appropriate according to different companies, so leave it to the companies, but at least asking them to satisfy at least one fairness notion is a reasonable thing to ask.
I can't tell who this is from. The notion of fairness is studied very well in philosophy. Is
Hmm.
literature from philosophy used in tackling these problems and algorithmic biases?
Oh, absolutely, absolutely. A lot of people from philosophy, and in fact, I haven't seen more diverse kind of academic people working in an area than algorithmic bias. I have seen philosophers, historians, economists, computer scientists, business school people. Everybody is, and it is important to have diverse set of opinions, because then we can, judge these fairness notions better. And philosophy has been like way ahead of us. Like they are the guiding torch for many of the researchers working in this area.
Fairness, yeah. Sonakshi says, how do you address network externalities in case of algorithmic bias?
So what kind of network externalities? Like
Okay, no follow-up questions because we have too many questions here. So I'll ask Sonakshi to write to you. Deepak says, Deepak Maheshwari, equal exposure fairness. In a way, isn't it akin to bridging the information
yes,
asymmetry?
yes. So it is. I wanted to call it information dissemination fairness, because it is not just about advertising. Advertising is only one way to inform people. There are many other ways in which we inform people, like writing blogs and writing posting the job posting in different platforms, and that way we disseminate the information, and that channel itself is also very biased and doesn't reach the right audience. So that gap also needs to be filled. So actually, earlier I wanted to put a title more about information discrimination, but then my co-authors pushed me out, focused on more.
Right. Could you please, Praveen says, could you please elaborate on the policy or law-based interventions to tackle AI bias?
So most of the push actually is coming from policymakers and law agencies. A lot of lawyers are also involved in this type of research, by the way, and but they are not the ones who are designing this fairness notion or analyzing them. They are uh, creating some kind of pressure for these firms to act, and that is probably the reason we are seeing such an overwhelming response from industry. In fact, in Amazon's case, Amazon went on to scrap one of its tool, which turned out to be discriminatory against females without any policymakers intervention. They did it on their own. So industry people are actually working very hard and on this problem, and I'm pretty confident that they will address it well.
Yeah. Okay, so there's a long question from Abhishek, but it's a combination of answers that you've already given
Hmm.
about the role of industry, about having a principle, about how to implement that. So I'll
Hmm.
leave that question unasked. So with this, thank you very much, Manmohan. It was really great. All of us learned a lot. I wish you had more time to present, the details of your paper, but I'm sure we'll be able to read your papers. And to the audience, thank you very much for joining. We will be posting this talk on our YouTube channel, and the slides will be up on our CEDA website, so you can access them. Professor Aseri's contact information is in the slides as well. So
Hmm.
please feel free to reach out to him about any more clarifications. And thank you very much, and thank you to the audience. Good night.
Thank you.